Hi everyone.
Your voice is quite the volume's low.
Yeah, is my voice, but also is my microphone for today. The laptop that I'm using. I'm going to do my best.
Yeah, no, that's better. So we've got Ekaterina, you're first, Josh Foster, I think you're second, then Tess, you're third, and then Josh Arnold's fourth, yeah?
Cool. Yep, sounds good.
So if my voice is a little bit low, can someone just give me a hint, a sign or something?
I think it sounds fine now, Kate.
Yeah?
Yeah, it's good now.
Don't worry about it. It sounds perfect.
We've had the go from Matt, by the look of it, from Dr. Matt White. So good morning, good afternoon, and good evening to PBTR attendees from around the planet. Welcome to this day 2 session of oral presentations on mechanisms, biomarkers, and technical apparel during heat and cold stress, which I think is the catch-all title for the sessions in the PBTR. My name is Jim Cotter. I'm an environmental physiologist at the University of Otago in New Zealand. A big thanks to Matt and his team in Vancouver for negotiating the untold curveballs and putting this conference together. Participating in PBTR always reminds us of how far away we are down here. But one silver lining of the virus is that in 2020, it's somehow closer and easier for us in the back and beyond. We're also fortunate that our Prime Minister, Jacinda Ardern, listens to scientists, which means that we've actually been able to continue on this year, for which we're incredibly fortunate, and we feel for those of you in countries with leaders who are less so inclined. Speaking of which, this session's being moderated by Dr. Roy Salgado. Roy hailed from California, and he then started moving east, completing his PhD in Albuquerque, and he's now relocated almost as far as is physically possible. He's working as an environmental physiologist at USRM in their Thermal and Mountain Medicine division. Our 4 speakers for this session are all from across the Atlantic in England, a land well known for its heat and altitude extremes. The first of which is Ekaterina Christogianni, and she has a background studying in Greece before she did her MSc in clinical neuropsychology at the Netherlands. And she's now researching somatosensory thermoregulatory aspects of neurological diseases, specifically in multiple sclerosis for her PhD research in the Thermosense lab at Loughborough University. She's presenting an aspect of that work today, and it's entitled Skin Wetness Across the Body of People with Multiple Sclerosis and its Modulation by Changes in Whole Body Mean Skin Temperature. Thank you, Ekaterina. We'll leave our session for a moment.
Mm-hmm. Okay, just to make sure everyone can see my screen. And everyone can hear me. Hi everyone, I am Kate, a PhD student from Loughborough University in the UK, and today I'm going to talk about one of my PhD studies. I'm going to discuss 2 things: the skin wetness sensitivity in people with multiple sclerosis disease and how this type of sensitivity is modulated when patient's skin temperature changes. So multiple sclerosis disease, or MS, is an autoimmune chronic disease of the central nervous system. The disease is notable for its erratic and unpredictable symptoms that is caused from the demyelination in the neural fibers in the brain and in the spinal cord. 80% of the symptoms are invisible to the onlookers, such as fatigue and body.
Sorry to butt in. I can't see your screen. Have you shared your application screen? I'm just wondering whether other people can't see it either. Are you trying to share your screen at the moment?
Can you see it?
No,
so
not yet.
Should I stop sharing and do it again then?
Kate, you need to share the application.
Yeah, I did. I think I have an issue with the laptop I'm using at the moment.
Okay.
So I'm gonna stop sharing and then do it again. Sorry about that.
We'll just stay online till we can tell you.
Yeah, I'm doing exactly the same thing now again. So please tell me if you can see my slides.
Yeah, it's perfect. Thanks.
Yeah, you can see it now?
Yeah.
Thank you.
Yeah, thanks.
So as I said before, I'm going to present one of my PhD studies about the skin sensitivities about people with MS. And 80% of the symptoms in MS are invisible. Invisible to the people that they don't experience them, such as body pain or body fatigue. And one of those symptoms is called wetness. This is being reported in websites and in research papers online, and is a sensation which is not unpleasant and spontaneous, and it happens without any skin stimulation. In one of our previous studies in the ThermoSense lab, we found some evidence that around 30% of the people with MS experience a phantom sensation on their skin that feels like water trickling on the skin while the skin is drying. However, we identified a major gap in the literature, and currently there is no information about how the MS-induced abnormalities affect the skin wetness sensitivity in people who have multiple sclerosis disease, and how this sensitivity is modulated when patients experience the temperature sensitivity phenomenon. So this phenomenon is a unique condition for people with MS, and is the worsening of the MS symptoms when the body temperature changes. In one of the studies we did in the ThermoSense lab, we found evidence that this sensation, this condition, can occur with changes in the skin temperature. Therefore, we created an experimental protocol that we induced only changes in the skin. So 12 people with MS and 11 gender and age-matched healthy controls participated in the study. They all remained seated on an armchair in a controlled environmental chamber of 24 degrees Celsius for 35 minutes. And when the 35 minutes were completed, the participants rated their wetness perception on visual analog scales that anchored from completely dry to completely wet. The thermal probe that you see on the picture was covered with a wet cloth and touched the skin on the forearm, forehead, and on the index finger in a dynamic fashion by applying 3 different thermostimulations, a warm, a neutral, and a cold one. So participants, they had to follow exactly the same procedure in a heat and in a cold condition. So first, they were exposed to 24 degrees ambient temperature, and then after that, the temperature in the chamber gradually increased in the heat and gradually decreased in the cold. For the data analysis, we followed an individualized approach in which we calculated the z-scores of log transform data. And we did that because we wanted to see how further away the MS patient data would be from the average values of the control group. So our experimental protocol successfully kept the rectal temperature stable in all the conditions in both groups, and induced changes in the heat with increases and changes in the cold condition with decreases. So here in the slide, I present the percentages of people and the number of people who reported wetness abnormalities, and this means that the people with MS reported gains and losses of this wetness abnormality. So they were hyposensitive and hypersensitive to wetness. So around 40% of the patients reported the wetness abnormalities during all thermostimulations. And the interesting thing was that according to the body region stimulated, we found a proximal to distal pattern of manifestation of those abnormalities. It seems that the further away a skin site was from the brain, the more the occurrence of these abnormalities to occur. So in the heat condition, 75% of the patients reported the abnormalities. They were pronounced in the cold stimulation, and the body region stimulated followed exactly the same pattern of manifestation that we saw before. In the cold condition, around 58% of the participants reported the wetness abnormalities, and again, those were gains and losses of wetness on the skin. And those were pronounced during warm stimulation. However, this pattern of manifestation was reversed here. It seemed like the closer a skin site was to the brain, the more the likelihood that the patients would report these abnormalities. So these results in this research show that, very importantly, yes, people with MS experience the wetness abnormalities. They are hypersensitive and hyposensitive to wetness, and that those abnormalities are modulated when they are exposed to heat and cold ambience. Very important, we found evidence that there is a relationship between the skin temperature and then the skin site that is stimulated with the brain. And then these results might have some implications for the patients, because they can explain how people grip, hold objects, and then they drop them from their hand. And we understand that this might cause confusion and then inactivity during the day. We also understand that these results can explain how people with MS regulate their thermal comfort, how they interact with objects and their immediate environment. So many thanks to all the people who participated in the study, that it was very difficult to be done, and my supervisors who supported the project, everyone who helped me with participant recruitment. Thank you very much.
Thank you, Ekaterini. Do we have any questions for Ekaterini? Something I've been wondering, I don't know much about MS, and there's a couple of things I'd be keen to know. There's two types of MS, aren't there? There's a progressive and a relapsing.
In my study, we did not take into account any specific type of MS. We currently have 3 of them. We have remitting, relapsing, secondary progressive, and primary progressive. But because we only have 12 people, we cannot make assumptions that people with remitting, relapsing, for example, would have more wetness abnormalities.
Right. So sometimes they can be free of symptoms, though, with the relapsing one, can't they? So could that account for some of the variability that you see with some people not experiencing it so much, or do you think it's just some people get it and some people don't?
So one of the requirements for the people to participate in the study was that they should not have any symptoms for at least 3 months. And we asked every one of them, and they confirmed that they didn't have any symptom, any relapse for 6 months. So the thing that we have to think is if the level of disability would affect in any way the wetness perception of the skin, because we had people with low disability and people with high disability that they were on a wheelchair. But again, you know, like when you have only two people that they have very high disability, you cannot again make the assumption that it will be worse for them.
Sure. Yeah. Yeah.
Hey, Jim. Sorry, I had technical issues. We do have a couple of questions from the audience. So, Ekaterini Lacey Alexander asked, what stage severity were the MS patients?
So we had 6 people with low disability. They were from 1 to 5.5. That means they were able to walk, they were able to drive, they are able to do their daily activities. However, they have like some cognitive and motor symptoms. And then we have the other half, the other part, we consider it high disability. They were around 6, from 5.5 to 7.
Okay. The next question is from Chris Minson. Do any of these responses in MS patients differ if their body temperature is elevated?
So the thing with this study is that we decided to just go out of the box and just followed another approach about the body temperature related issues in MS. And actually we had a study that we showed that changes in the skin temperature can create this unique condition, this temperature sensitivity phenomenon. So when this thing happened, when the patient's skin temperature increased and decreased in both of the conditions in the study, and this was plus minus 4 degrees in both of the conditions, we saw that there were a lot of people, and you saw the percentages, they were maybe half of the people, 20 to 50%, that they reported those abnormalities. So that we see that the skin temperature can make a difference.
And I believe that's all we have, Jim.
Thank you, Ekaterini. Thanks very much for that.
Thank you.
So our second speaker this morning is Dr. Josh Foster. Josh did his PhD at the University of Bedfordshire, and he is one of the people who work across both Ps and PBTR. Like Ekaterini, Dr. Foster is working in the Environmental Ergonomics Research Centre at Loughborough University. He works in occupational heat stress physiology, and that's including the effects of PPE use for COVID. Today, he's presenting a study on the impact of solar radiation on human physical work capacity and the heat interactions between clothing, air temperature, and humidity. Thanks, Josh.
Excellent. Thank you very much, Jim. So just to provide some background to our study, we know that heat stress reduces human physical work capacity, and that has quite large implications, especially from an economic standpoint, and that's received a lot of attention, especially in the climate change literature, in terms of predicting future GDP losses with the reduction in physical work productivity in certain industries. We've made quite extensive efforts in our lab over the last few years to try and model this empirically based off data obtained in environmental chambers. And what we've obtained so far is an enormous amount of data from several hundred trials in which we can predict human physical work capacity with equations which include either air temperature and humidity combinations, or with a suite of different heat stress assessment metrics, in this case, such as the wet bulb globe temperature. So hopefully we see that work out in the next couple of months. However, there's rather little known in the literature about the performance losses linked to increased solar radiation exposure. Some of the best sort of proof of concept evidence we have for this was provided by Atani in 2016, who showed a rather linear reduction in the exercise time to exhaustion as a function of the total solar heat load. However, that was at a fixed air temperature and humidity combination. So having said that, there is little known about the dynamic nature of the effect of solar radiation on human physical work capacity, especially with changing air temperature, humidity, and with different clothing types. So this work's highly relevant to different occupational scenarios. So to help answer this question, we collected data in an environmental chamber with the use of solar simulation lamps, which have a similar spectral content to that of sunlight. And we used a physical work simulation for 1 hour to test the performance differences. I'll talk about that more in the next slide. We collected data from 14 participants who were purposely recruited to be heterogeneous in their body characteristics and aerobic fitness levels. We collected data in dry heat, so 20% relative humidity, in temperatures spanning 25 to 45 degrees Celsius air temperature, and also in humid heat, so 80% relative humidity in temperatures spanning 25 to 35 degrees Celsius air temperature. So from the 14 participants, they were separated into either participating in semi-nude conditions, so that's just with shorts and trainers, so much of the skin area exposed, directly exposed to the solar radiation, and half were sort of partitioned into the coverall condition, so around 0.86 clo with the high clothing coverage condition there. So they completed trials in the aforementioned environments with 2 radiation intensities. So the within subjects component of the study was completing trials with the solar lamps switched off, so in a shaded condition, or with the solar lamps switched on. And the intensity of the solar radiation was around 800 watts per meter squared, and the skin surface area which was projected or exposed to that solar radiation was around 0.5 meters squared. So just briefly on the protocol, we have presented this before at a number of different conferences, including the last PPTR. We used a 1 hour treadmill walking protocol at a fixed heart rate of 130 beats per minute. All participants performed this trial in a cool environment with no heat stress, and then it was repeated under a number of different heat stress conditions, like I described in the last slide. So we calculate the total energy expenditure in the control trial and then in the heat stress conditions, and the performance in the heat stress conditions is then expressed as a percentage. So just to briefly show that graphically, we can see across the 1 hour, the heart rate is fixed at 130. There's an upper limit on the speed of the treadmill to ensure that the exercise was maintained at a walking pace. And then the grade was freely adjustable to ensure that the heart rate was fixed at the 130 cutoff. And that was automatically controlled by the treadmill algorithms. So in that scenario, 2,200 kilojoules of net work above resting was performed. Again, we complete this in a number of different hot trials. So in this example, again, the heart rate's fixed, the speed starts to come down towards the end, and we can see a large reduction in the grade profile to ensure that that heart rate is maintained. And so in this scenario, if we have 1,500 kilojoules of net work performed, that's a 32% reduction from the control trial. And we then conclude that physical work capacity is 68%. Just briefly, the fixed heart rate was chosen due to a number of supporting studies, a large-scale field study showing that if workers are allowed to self-pace, they'll typically do this based off their working heart rate. So moving on to some of the results, and we'll focus first on the dry climate. So this data is that of which in the low clothing coverage conditions, so just with the shorts, we found no effect of solar radiation at 25 and 35 degrees Celsius air temperature. However, we saw a significant reduction of around 5 to 10% at 40 degrees Celsius, and this grew exponentially larger at 45 degrees Celsius. So at 45 degrees Celsius with low clothing coverage, there was around a 40% reduction in physical work capacity elicited by the solar radiation lamps. In the high clothing coverage condition, there was no effect of the solar at 25 degrees Celsius. However, thereafter, there was around a 10 to 15% reduction in physical work capacity in the remaining conditions tested, so from 35 to 45. However, in the high clothing coverage condition, we didn't see that exponential reduction. When we move into more humid climates, there was a rather consistent reduction in physical work capacity elicited by solar radiation at around 10 to 15% again. And similar story was true for the high clothing coverage condition. Slightly lower absolute losses in physical work capacity, but it was quite consistent across all of the different conditions. So if we look at some of the physiological manifestations of why that is, we found very strong links between the absolute skin temperature and physical work capacity within solar radiation trials and within the shaded trials. And we can model or predict physical work capacity quite accurately, even if we just use skin temperature as the input variable. However, you'll notice on the right that rectal temperature, at least in activity levels simulating occupational workloads, has very little predictive power. In fact, I'd go further and say it has no predictive power for estimating physical work capacity. If anything, we saw the lowest rectal temperatures at the lowest levels of physical work capacity, and that would reflect the very low work rates performed in the hottest conditions. Another way in which we can use the data is to model the impact of solar radiation on physical work capacity for heat stress assessment metrics that don't actually account for that variable. So for ones that do account for solar radiation, such as the wet bulb globe temperature, we can see that even if we pull all of the data together, we're able to predict physical work capacity rather well, regardless of whether the trial was conducted in solar radiation conditions or in shaded conditions. So what you see in the red arrows here is the direct effect of solar radiation for the same environmental condition. And as you can see, the WBGT value shifts to the right when we're exposed to solar radiation due to the change in the globe temperature. However, if we look at a heat stress assessment metric that doesn't account for solar radiation in its calculation, the heat index is a good example of this, where it only takes into account the air temperature and humidity. We can see that we require two different models to explain the responses, whether we're simulating indoor or outdoor environments. But what we've been able to do with this, and again, hopefully work that's going to be published in the next few months, is we've been able to mathematically model the impact of solar radiation for the prediction of physical work capacity. So regardless of whether the condition's indoors or outdoors, we should be able to model that and predict that for any heat stress assessment metric, regardless of whether it accounts for radiation or not in its calculation. So just to summarize, the impact of solar radiation on physical work capacity depends on the air temperature firstly. We found an exponential reduction in physical work capacity in very hot environments, so above 40 degrees Celsius. In high humidity conditions, the reduction in physical work capacity with solar radiation was quite consistent across clothing conditions and air temperatures. And clothing had a beneficial effect, so wearing the coveralls had a beneficial impact only in very hot environments. So in quite specific scenarios, the high clothing coverage is sort of blocking the effect of the radiation compared to wearing no protective clothing. We showed that at the workloads we employed in this study, which reflect occupational heat stress, mean skin temperature is a very strong predictor of physical work capacity, regardless of whether you're looking at that in shaded or unshaded conditions. And we can use the data collected to inform correction factors for heat stress indices that do not account for solar radiation. So I'd like to thank my collaborators, all of the participants in the study, and the European Union for funding the work under the project name Heat Shield. Thanks. That concludes.
Thanks, Josh. That was excellent. Thanks for sticking to time too.
All right, Josh, you have a few questions here. Lacey Alexander asked, why did you project radiation over a fixed area instead of as a percentage of body surface area?
I'd say more for practical reasons mainly. I think we were primarily interested in the total wattage of the solar radiation lamps. I'm not sure. I think if you're to project the radiation onto a fixed percentage of the body surface area, that would require a different setup for different morphologies of the participants. I think that would be quite difficult in practical terms.
Okay. Rebecca Ralph asks, do you think your findings would be the same if you conducted the study in females as well?
Yeah, so I think in terms of the heat stress response in females versus males, they're generally quite subtle, and you have to have quite carefully designed experiments at quite high workloads or quite high heat loads in order to detect differences. At least that's what we concluded in a recent literature review we published in Frontiers in Environmental Physiology. The protocol responses are highly dependent on the fitness level. So we actually have a paper coming out where we're modeling the impact of fitness on the responses of those physical work capacity curves. I can't guarantee that there won't be an effect of sex at certain levels of heat stress. We weren't able to study that at this time, but I think a big chunk of the variation in the data is explained by the variation in fitness levels.
All right, Jim, do we still have time for a couple more questions?
Yep.
Okay.
There's another one there that's very similar, just in terms of more heterogeneous, younger and older. If you want to wrap that one in with it.
I don't see it. Is
okay,
it from
so
Ash?
let's carry on down linearly. Yep.
Okay. So Hayden Hess asked, what was the relative exercise intensity for fixed heart rate at 130 beats per minute? Did you anticipate that your data show exaggerated response effect on solar radiation?
So if I understand that correctly, I think that refers to maybe the percentage of VO2 max that's performed at 130. And again, that depends on the environmental conditions. So in the coolest environment, that would be broadly approximate to around 50% VO2 max. I'm just here seeing Chris Minson isn't hearing the responses to the questions. Is my mic working okay?
Yeah, it's fine.
Yes, it is.
Okay. And again, that would change. That would certainly change as a function of the overall heat stress, because you're performing less work for the heart rate. We see when we separate the responses based off the fitness levels, we see a sharper reduction in physical work capacity towards the upper end of the heat stress. So that probably does reflect higher body temperatures in the people who are working harder. So I think that there probably is an interaction, but at the upper levels of heat stress.
Okay.
There's some more good questions there, but you might have to address those offline. Sorry, we probably should try and stay on time and keep going. But thank you very much, Josh.
Thank you.
So now moving away from Loughborough briefly, we're going to Chichester and for a presentation by Tessa Flood. It's some of her PhD research within the Occupational Performance Research Group there. Tessa's research background also spans both physiology and pharmacology. I see she's even studied New Zealand black currant. And her research focuses on sex differences and the influence of menstrual cycle and hormonal contraceptives on exertional heat illness during uncompensable heat stress. The presentation today is on whether wearing additional clothing impacts on gastrointestinal function and microbial translocation in response to exercising in uncompensable heat stress. Thank you very much, Tessa. You're right to share your screen?
Yeah, I think that's shared now. Perfect. Thanks for the introduction, Jim. So as Jim just said, I'm going to be talking about the impact that additional clothing has on intestinal fatty acid binding protein and soluble cluster differentiation 14 responses following exercise and uncompensable heat stress. So before I get started, it's important to think about what actually is the problem here and how can we investigate it. So we know that there's a high amount of individuals that work within physically demanding occupations, which then can increase their risk of exertional heat illness. We also know that there's a change in climate at the moment. We're getting increases in excessive heat exposures. Many of these individuals that work in physically demanding occupations need to wear additional clothing to obviously complete their jobs. We know that clothing exacerbates heat strain. This is well documented in the literature, but what we don't know is how this then affects the exertional heat illness biomarkers. So to look at this more closely, I'm going to be talking and referring back to the gastrointestinal pathways of exertional heat illness. So what I'm going to do first is just talk you through the diagram that I've put up. So when we start to exercise in the heat, we essentially cause hypothermia, so that increase in heat storage and deep body temperature. So what this does is this causes a reduction in GI blood flow. So essentially the blood flow is moving away from the gut towards the muscle and the skin. So what this does is we get a reduction in GI blood flow, which causes hypoxia within the gut. And what this starts to do is it causes gastrointestinal damage. Essentially, gastrointestinal damage is caused by the tight junction proteins opening within the intestinal epithelial cells. So when these tight junction proteins start to break down, we get a translocation of endotoxin. So when I talk about endotoxin, I'm talking about lipopolysaccharide or LPS. So when LPS translocates from the inside the gut into the circulation, we know it binds to toll-like receptor 4. So when it binds to toll-like receptor 4, it essentially starts to cause this acute phase inflammatory response, which, if left untreated, can lead to the more severe consequences of exertional heat illness. So how can we start to actually measure this? So the first thing we can obviously do is measure your physiological responses to the exercise and the heat stress. So we can measure things like your rectal temperature, we can measure heart rate, how hard someone is working, and the amount of heat storage that someone gains during the heat. And then what we can start to do is look at the biomarkers that can be associated. So I'm going to focus on two main biomarkers of these pathways today. So the first one is intestinal fatty acid binding protein, which is a marker of gastrointestinal damage within the gut. So I'll call this IFAB for the rest of the presentation. So what we can also do is look at biomarkers that occur further down the pathways of gastrointestinal damage. So essentially we can look at soluble cluster differentiation 14, or CD14 as I'll call it, which is an indirect marker of LPS translocation. So essentially when LPS translocates from the gut into the circulation, soluble CD14 is involved in the binding of LPS to toll-like receptor 4. So essentially what we should see, if there's a higher level of microball translocation, so translocation of LPS into circulation, we should see an increase in soluble CD14 within the gut, within the blood. So the aim of the study was just to quantify gastrointestinal damage and microball translocation via the measurement of IFAB and soluble CD14 following exercise in uncompensable heat stress while wearing two different clothing ensembles. So to do this, we had 8 participants who were unmatched for body mass, size and fitness. So they came into the lab twice in a crossover design, and we completed exercise set by watts per kilo of metabolic heat production to account for the unmatched population that we had. And they completed 2 trials, either wearing coveralls or just wearing shorts, as described in the previous study. So as you can see from my table on the right, we do have quite a large range of participants, especially within body mass, body surface area and aerobic fitness. So when our participants came into the lab, they came in following a 12-hour fast. We obviously kitted them up with their rectal, skin temperature, heart rates. We did a preliminary hydration assessment, and then we did a 20-minute rest on a resting bed. in an air-conditioned lab before we took our baseline venous blood sample. We then moved our participants into the chamber and gave them a 10-minute stabilization period. They then completed their exercise wearing either the coveralls or the shorts, which they walked with a combination of speed and gradient to exhaustion, set at that 7 watts per kilo of heat production. We gave them set amounts of water throughout, based on body mass, and we used Douglas bags to confirm our watts per kilo, which were set at 7 and maintained at 7 for the whole trial. Once they reached exhaustion, they were sat back down, and we took a venous blood sample and physiological measurements at 5 minutes following exercise, 30 minutes following exercise. We then moved them back into the air-conditioned lab and cooled them for half an hour until their core temperature was back to around 37 degrees, and we took our final venous blood sample. So what did we see? So firstly, we'll start with the amount of work they were able to complete in the trial. So work obviously reduced when wearing the coveralls across all our participants by around 102 kilojoules. So all the graphs that I'm going to show in the next few slides, the coveralls are the grey bars, the shorts, the white bars, and then the individual lines are our individual participants' responses. So when we move on to our physiological responses, we see that overall we had an increase in both rectal temperature and physiological strain index, which was reflected across the majority of our participants. So we saw a 0.24 degree rise in peak rectal temperature and a 0.5 increase in physiological strain index when wearing those coveralls. So what I'd like to bring your attention to, especially, is the rate of change of our core temperature. So as I said on the last slide, we reduced the amount of work they were able to complete when wearing the coveralls. This essentially meant that they just got hotter quicker. So we had an almost double rate of rise in rectal temperature across the coveralls than the shorts trial. So we obviously expected that when we were adding the coveralls, we would exacerbate the heat strain and thermal strain caused. And what I'd also like to just mention here is that we increased their thermal comfort scores. So participants were feeling particularly uncomfortable wearing the amount of clothing, which potentially may have led to some earlier trial terminations. So when we start looking at our biomarkers, we have our IFABs. These are presented as change from baseline results. So we see an effect of time, so increase from baseline. We see no difference between the coveralls or the shorts conditions. What I would like to bring your attention to here is the large variation we saw in the IFAB responses, potentially due to the unmatched population. What we also wanted to do was to account for the fact that this was a time to exhaustion trial. So to do that, we looked at the integrated area under the curve for both responses. And what you can see is that there's basically no difference between those two conditions. So again, coveralls are the grey bars and the individual lines, your individual participant responses. Again, we're seeing very varied responses between the participants, with some participants seeing very little change in IFAB responses. When we move on to soluble CD14, the graph is presented in the same way as the IFABs. We're looking at change from baseline. We see again an effect of time, but no effect of condition, despite the fact that we're seeing a slight reduction in the shorts trial. At 30 and 60 minutes, the variation is large within these responses. So overall, we see no difference between them. Again, when we present as integrated area under the curve, we're seeing some very large variation in the responses, but essentially no difference between the response for coveralls or for the shorts trials. When putting this together, when we added the coveralls, we decreased the work completed, we increased their peak rectal temperature, and we increased their physiological strain index. We saw no difference in intestinal fatty acid binding protein or soluble cluster differentiation 14 when presented either as change from baseline or as integrated area under the curve. So in conclusion, we can state that when we added the additional clothing, we exacerbated heat strain across the majority of our participants as expected, but potentially due to the large variation in the responses and the work completed, potentially due to this unmatched population, we do not influence the degree of gastrointestinal damage or microbial translocation experienced following exercise in this particular population. I'd just like to say thank you very much for listening. Happy to take any questions. I'd just like to say a huge thank you to my supervisors, so Sam, Steve, Ella and Ben, and to my help in the lab, so my 2 work placement students, Beth and Georgia, and Stephen Stefano. Thank you very much.
Thanks for another great presentation, Tess, and thanks again for staying on time.
So, Tess, we have one question from Vania Brunt. Is there any evidence that differences in gut microbiome composition can protect individuals who may be at greater risk of exertional heat illness, or who may have more severe responses, e.g., greater gram-negative bacteria?
That's not something I've necessarily thought about yet. That's something I definitely start to look into, as this is just the beginning of starting to dig into this for my PhD. So yeah, thank you.
We also have a question from Chris Minson. Has it been determined that the gut actually becomes hypoxic in this situation? If so, could the degree of hypoxia of the gut be a factor to help explain the variability in your data?
So we do have some research that has started to look at the extent of this within the gut. So measuring perfusion rates following exercise, and obviously needs to be more work in the heat. Obviously, yes, I totally agree that the degree of that factor would influence the variability. And that's something we're especially interested in, especially with the IFAB responses, because we're seeing quite large variation in comparison to some other studies. So it may be that that marker in particular has more variation in it than some of the other biomarkers, especially in the unmatched population groups, so with different body mass and sizes.
Thank you, Tess.
Cheers.
Yes, am I correct? They all walk to exhaustion in both conditions. So the fitter people had to walk further, and the people had to walk further if they're wearing the lower clothing ensemble. So do you think that's a factor? Like if everyone had done the same task over the same duration, the fitter people may have had less translocation and the lower clothing may have had the same effect. Would that be reasonable?
Definitely, potentially, yes. And that's something we have considered going forward, and we've actually started to change our model very slightly going forward in our studies to set the exercise time. So we wanted to use the open-ended model to try and get the higher rectal temperatures.
Sure.
So we're getting people to that exhaustion criteria, but yeah, we are aware of the limitations and the fact that we're probably adding some variation in by letting people walk to exhaustion.
Yeah. Thank you very much for that.
Thank you. Cheers.
So our final speaker for this session is back to Loughborough University now, and that's for Josh Arnold's talk. Josh literally lives, breathes and dreams multi-stressor and extreme environments. He studied at Sheffield, Hallam and Bangor universities. He worked in outdoor centres, the Ministry of Defence. He circumnavigated the planet in a yacht. He cycled around Iceland. He's climbed over 6,000 metres in Bolivia. Now he's back to Loughborough, and he's completing his PhD with Simon Hoddett and Alex Lloyd. And he's going to present a PhD project on the independent and combined impact of hypoxia and acute inorganic nitrate ingestion on autonomic thermoregulatory responses to the cold this time. Thank you, Josh.
Thank you very much for the kind introduction, Jim. So I'm Josh Arnold from Loughborough University, and good evening from the UK. Okay, so firstly, to take you into a bit of context. So how do we respond to the cold? Well, our autonomic response to the cold is primarily a function of two things: heat conservation, peripheral vasoconstriction that is, and heat generation, shivering thermogenesis. It's worth considering that in reality, cold stress is rarely experienced in isolation. And specifically, my research interest is that of combined hypoxic cold stress and how this modulates our response to the cold. If we look back at the previous literature in this area of hypoxic cold stress, we can see that when cold stress is combined with hypoxia, researchers observe both blunted vasoconstriction and suppressed shivering thermogenesis. While the underpinning mechanisms remain unclear, nitric oxide availability appears to regulate the hypoxic cold response. Amongst a number of modalities we can use to investigate the hypoxic cold response, dietary nitrate ingestion provides both a safe and convenient way to increase nitric oxide bioavailability and therefore allows us to assess the interaction between cold and hypoxia. As such, based on the previous literature, the aim of this work was to assess the impact of normobaric hypoxia and acute nitrate ingestion on shivering thermogenesis, cutaneous vascular control, and ultimately our thermal response to whole body cooling. With this aim in mind, we formulated two hypotheses. Our first hypothesis focused on the rate of heat loss, and we conjectured that we'd see increased peripheral heat loss with hypoxia compared to normoxia, and that this response would be synergized, augmented with nitrate ingestion compared to a placebo. Looking at our shivering response in our second hypothesis, we conjectured that we'd see no difference in the temperature threshold for shivering with hypoxia compared to normoxia, yet we expected to see an earlier shivering onset due to faster heat loss, as explained in hypothesis 1. And again, this would be synergized by nitrate ingestion compared to a placebo, as explained in hypothesis 1. And we hope that the findings of this work would both infer or improve our understanding of mechanisms, but also translate to clinical context and also occupational context where possible. So with the study aim in mind and the hypotheses, how did we approach the study design? We recruited 11 young healthy volunteers, and we exposed them to whole body cooling at 10 degrees ambient air temperature across 4 visits. The 4 visits comprised our experimental conditions, which were varying combinations of normoxia and hypoxia, and placebo ingestion and nitrate ingestion. So if I take you into one of these visits and show you what they look like in terms of the actual experimental protocol. So this is a schematic of the protocol. Okay, so firstly, if we look at the top, so 2 hours prior to visiting the lab, participants ingested either a nitrate active shot or a nitrate depleted placebo shot. They then entered the lab and underwent a 30-minute preparation phase, also allowing skin temperature to stabilize and allowing us to append all the probes. 2.5 hours post-ingestion, individuals then entered the cold chamber and were progressively cooled for the rest of the trial. During cooling, individuals laid supine on a water-perfused bed, inspiring either normoxic or hypoxic gas, offered through Douglas bags. And interesting, we should note that the normoxia was also offered through the Douglas bags to try and wear best possible to provide some sort of placebo effect. The hypoxia was offered as an FiO2 of 0.13, equivalent to about 3,750 meters. Finally, individuals were left to whole body cool until they were seen to be continuously whole body shivering via visual assessment. We were then left them for an additional 15 to 20 minutes, at which point we removed them from the cold and actively rewarmed them with careful monitoring. So within the protocol, what did we actually analyze? So our outcome variables, firstly, shivering onset. So we assessed shivering activity via 3 metrics: VO2, electromyography, and also mechanomyography. Looking at specifically at shivering onset, we looked at these 3 variables over time, looking for an inflection point in the data. So in accordance with a previous paper we published earlier this year, we analyzed the inflection point as per a mathematical method, segmental regression, and also visual inspection of graphs. So the combination of these 3 metrics and the 2 analyses gave us 6 values for each independent trial. We used a mean to generate a single value for shivering onset per trial per participant. In terms of the vascular response, we looked at skin blood flow via laser Doppler flux, and then we also paired this with blood pressure to give us cutaneous vascular conductance. In terms of our thermal response, we looked at mean skin temperature across 14 different sites, and we also looked at rectal temperature as a proxy for our core temperature. Interestingly to note, so in terms of the thermal responses, the skin temperature and rectal temperature, we analyzed these both as a rate of change and also at shivering onset. So we used a fixed analysis at 45 minutes, looking at the delta from baseline. And we also looked at the delta relative to shivering onset to the trial-specific shivering onset to look at the thresholds. All variables were assessed using a two-way repeated measure ANOVA, 2x2 design, with the hypoxia and nitrate ingestion as the independent factors. So what do we find? Firstly, looking at shivering onset. So this figure shows us our experimental conditions down the y-axis, and also shivering onset time in seconds along the x-axis. Our independent effect for hypoxia, we saw that hypoxia significantly decreased shivering onset time by approximately 10%. Alternatively, and interestingly, we saw that nitrate ingestion actually increased shivering onset time by 15%. No interaction was observed between hypoxia and nitrate ingestion on shivering onset time. Looking at our vascular responses. So just a snippet of the laser Doppler flux with our conditions along the x-axis this time. We saw the hypoxia significantly increased skin blood flow, and we also saw the increased vasodilation as per our CVC results. On the other hand, this time, we saw no main effect for nitrate ingestion on either skin blood flow or vasodilation. No interaction was observed between hypoxia and nitrate ingestion on either of the vascular metrics. Finally, our thermal response. So just a quick reminder of the two different analyses, the fixed and also the relative to shivering onset. So we saw no, interestingly for skin temperature, mean skin temperature layers, we saw no effects across either analysis or for either independent factor, hypoxia or nitrate ingestion, on in terms of skin temperature. Alternatively, we found some interesting results for rectal temperature, which is good. So looking at the left-hand panel first, which was relative to shivering onset, we saw that at shivering onset, nitrate significantly reduced rectal temperature compared to a placebo, yet no main effects were observed for hypoxia compared to normoxia. That is relative to shivering onset. In a bit of a role reversal, if we now look at the right-hand panel, looking at the fixed time window analysis, thus a proxy for heat exchange, we saw that at 45 minutes, hypoxia significantly reduced rectal temperature compared to normoxia. Yet, alternatively, no effect was seen for nitrate ingestion. Again, no interaction was observed between hypoxia and nitrate ingestion on the delta changes. So bringing it all together into our discussion points. So across metrics and across analyses, we observed no interaction between hypoxia and dietary nitrate ingestion on our thermoregulatory response to the cold. If we look independently at the factors, so we saw that hypoxia significantly reduced shivering onset time, and we proposed that these mechanisms were mediated by an increase in peripheral heat exchange, yet were independent of any change in the central thermoeffector threshold. For example, a matched core temperature at shivering onset. Alternatively, and interestingly, against our conjecture, we saw that nitrate ingestion significantly increased shivering onset time, and we think that the mechanisms are mediated by a change in the central thermoeffector threshold, i.e. a lower core temperature at shivering onset, and that any change in the nitrate with the nitrate ingestion was independent of peripheral heat exchange, i.e. matched skin blood flow, matched CVC, and also matched rectal temperature at 45 minutes. Thus, to conclude, we propose that hypoxia modulates the thermoregulatory response to the cold, and it does so independent of any nitric oxide bioavailability from the nitrate reduction pathway. Thank you very much.
Thank you.
So no questions from the chat, Josh, but I do have a question for you, if you don't mind. A really good presentation. Just curious, as you use normobaric hypoxia, do you think there would be any differences if you used hyperbaric hypoxia?
I'm not sure in this. I'm well aware of there's a lot of literature comparing normobaric and hyperbaric hypoxia. off the top of my head, I don't know what it would specifically do to our findings. But I'm sure there's debate as to whether they are similar or whether they're not. I'm not sure. It'd be good to talk to you about that afterwards, actually, and see sort of your thoughts on it if you have that. But I can't differentiate what that would do to our findings at present.
Yep, no problem. We could definitely talk offline on that, Josh.
Yeah,
Thank you.
sure.
Oh, actually, we have one question from Daniel Gogan. So thanks, Josh. I may have missed this, but how does hypoxia increase heat loss in an environment if it does not affect skin temperature?
So this is interesting. So as I suggested, we'd found no difference in the skin temperatures. And this was actually quite surprising to us because we used a ISO standard 14 site mean skin temperature assessment. So we assumed, and we think we should have observed a difference with the increased skin blood flow, the changes in rectal temperature, but there was no change in the skin temperature. Therefore, we think there may be some sort of measurement error there. So looking back at the literature, and I think there's some papers by McCrae that discuss that when you have a large difference between your ambient environmental temperature, perhaps, and your skin temperature, actual increase in the error of measurement, that is, with skin temperature potentially increases. Whether that stops us from observing like specific statistical changes, I'm not sure, but yeah, I think it's more methodological, the lack of response with skin temperature rather than actual physiological.
Okay.
We're 1 minute past, but we also started slightly late. We've got one more question. Do you want to take that, Roy? And then I think Matt's going to jump in for some notices before the end of the session. Thanks.
Yes. So Adam Seller says, nice job on presentation. I'm wondering if the nitrate supplementation altered VO2 during the cold, and so explaining the increased shivering onset. I'm wondering if shivering onset is still increased after nitrate supplementation when using only EMG and MMG to determine shivering onset.
So we looked at these. We actually looked at in a sort of sub-analysis, we looked at the mean VO2, for example. I think this answers it. The mean VO2 over the course of the cold stress, or at 45 minutes as well. We saw no differences with nitrate ingestion or no main effects. So I think from that you can infer that there wasn't any alteration of VO2 during the cold stress with nitrate compared to placebo. But yeah, again, it'd be good to discuss those sorts of things afterwards, maybe.
Thanks very much, Josh, and to Roy for fielding the questions, and to the audience for all the good questions during the session. Thanks to everyone for sticking to time. And I think Matt White is jumping in here just for a few notices. Thanks. Matt, are you there?